on this idea of Gram-Schmidt orthonormalization. So before we proceed to that, it is important to distinguish between say 2 points. So linearly independent vectors and orthonormal basis set. Okay, and like this, I would try to motivate by an example. So let me take up an example where I consider a ket psi1, which is a column vector 1 1 1. Right, so the number of rows are 3, number of column is 1, so it's a 3 cross 1 vector. And I consider two other vectors, psi2, which is like 1 1 0 and psi3, which is, let's construct it slightly. Okay, so let's construct it like 1 0 1. So let me see. It looks like somebody is waiting in lobby, and disturbance will keep on happening because students are not disciplined to be on time. So thank you for unmuting yourself. Please mute yourself back. That does not help anyone. Okay, so the point that we were discussing was we need to distinguish between these linearly independent vectors and the orthonormal basis set. So when we say span of a given vector space, so it turns out by using a suitable set of linearly independent vectors, right, of the right dimensionality, right, one can actually span a given vector space. So for example, 1 1 1 column vector, which is psi1, similarly psi2 and psi3, these three are linearly independent. You can check that. You can never write psi3 is not equal to a psi1 plus b psi2 for any choice of a comma b. Okay, so whatever a comma b you choose, you would never be able to write psi3 as a linear combination of psi1 and psi2. And similarly, you can also show that psi1 is not equal to, say, let's say a psi2 plus b psi3, and psi2 is not equals to a psi3 plus b psi1. So whatever be the choice of a, b you make, you will never be able to write psi1, psi2 or psi3 in terms of the other two vectors. So in such a scenario, you can call them to be linearly independent, but that provides you the strength of writing any arbitrary vector, say 1, 2, 3. But say a typical vector belonging to the same vector space, say 1, 2, 3, can be written as a psi1 plus b psi2 plus c psi3. So in fact, psi1, psi2, psi3 can span the vector space. So like it is not very hard to find what A, B, and C would be. Say for example, if I'm just trying to figure this out, this is going to help me into writing A plus B plus C, and this is going to be A plus B, and this is going to be A plus C. So if I satisfy A plus B plus C equals to 2, equals to 1, A plus B equals to 2. So if A plus B equals to 2, it implies C equals to minus 1, right, straight away. And if C is minus 1, then the third equation tells us A has to be 4. And if A is 4 and C is minus 1, so 4 minus 1 is 3. So minus 2. So B equals to minus 2. So therefore, that's how you will be able to, we can check A plus B is 4 minus 2, which is 2. So a choice of A, B, C as 4 minus 2 and minus 1 helps us to write this typical vector 1, 2, 3 into this form. But we can observe that, so let me see if somebody is in the lobby. Nobody is in. Yeah, there are people in the lobby. Yeah, so but we can clearly observe that if we are trying to say psi1, psi1, right? Psi1, if you see, it is going to be 3. So it is not equal to 1, right? And also psi2, psi2 is not equal to 1, and psi3, psi3 is not equal to 1. That means they are not normalized, but at the same time you can also see that, so therefore these are not normalized. So let us just try to see not normalized. Okay, and also one can see that they are not orthogonal, they are not forming an orthogonal basis. So for example, psi1, psi2 is not equal to 0, right? You can make out psi1, psi2 is going to be 2, psi2, psi3 is again going to be, psi2, psi3 is going to be 1, and psi3, psi1 is going to be 2. So psi2, psi3 equals to 0, and psi3, psi1 equals to, just see, psi3, psi1 is equals to again 2. So therefore, like taken together, they're not really forming a, not forming orthogonal, so a set of orthogonal vectors. Not forming a set of orthogonal vectors. And the question is, so the important question, so I think we again have someone joining in the lobby. Excellent, people can join, walk in without any concern for their fellow classmates. Yeah, so the important question now is that given psi1, psi2 and psi3, can one, and I would rather say how can one find an orthonormal basis set? Okay, the only thing that is ensured here is these are linearly independent. So as we just now saw, like the psi1, psi2, psi3 were linearly independent, but then they were forming a basis set, but that basis set was neither having vectors which were normalized nor having vectors which were truly orthogonal to each other. So therefore the question here is, salient question is, how do we really find the basis set? So now the procedure, I would just write down the procedure here. Let's just choose black color. So the procedure here to find this basis vector is like, let phi1, phi2, phi3 constitute the corresponding orthonormal basis set. Fine. So now how do we obtain it from psi1, psi2, psi3? So step one is we designate phi1 as psi1 divided by norm of psi1, which is like psi1 divided by dot product of psi1 with psi1, but taking the positive square root of that. Okay, so this is how you would immediately write down the first member of the orthonormal basis set. Now, in order to find the second member, phi2, what you need to do is you take psi2, but subtract the projection about the projection. So you have to write down a projection operator of phi1, right? So we will introduce this. So right now we are just writing or claiming that this is called the projection operator. So as if this is projecting out the component of psi2 on, so okay, so here it's better to use the black color just to avoid confusion. So projection operator is only the one which is kind of earmarked with this bracket. But what it does is it projects out the component of psi2 along phi1 and subtracts it from psi2 and then take the norm of this quantity with psi2. So basically what we do is we take a norm of psi2 with this entire quantity. So basically psi 2 minus phi 1. Okay, so here we have to be careful that this is a outer will. Okay, so we will soon describe what an outer product is for notational convenience. Phi 1 and then psi 2 and take the square root of this. So this is how this second vector is going to look like, and a step of simplification would tell us that this is essentially psi 2 minus. So this dot product of phi 1 with psi 2 is going to be a number, right? Whether complex or real, but it is going to be a number. And then we are left with a ket this. So this is allowed because phi 1 psi 2 is a number. Number commutes with a vector. Okay, and in the denominator it is going to be psi 2 minus. Now you can see it is going to be psi 2 phi 1 once and phi 1 psi 2. So it is as if this is going to be phi 1 psi 2 multiplied with its complex conjugate. So therefore this is like mod square of this and take a square root of this. So this is how we are going to define phi 2, right? And then once we have this phi 1 and phi 2, we have to simply repeat this process of projecting out components along already known vectors. So phi 3 is going to be psi 3 minus, you will project out component along phi 1 of psi 3 and component along phi 2 of ket psi 3. So that is how it is going to look like. And then you will have to find the norm of this. So that essentially means you are going to take psi 3 and operate it on this quantity psi 3 minus phi 1 psi 3 minus phi 2 psi 3. Right, so this essentially is the recipe, and a single step of simplification would tell us that this is like finding psi 3 minus a component along phi 1. So because phi 1 psi 3 dot product is a number, so it's like phi 1 psi 3 about phi 1 and minus phi 2 psi 3 along phi 2. Yeah, so that is what it would be, and then divided by this entire thing could be psi 3 and you will have to subtract. So here you can see that psi 3 acts on phi 1. So therefore it is like phi 1 psi 3 multiplied by its complex conjugate. So therefore you will have a minus of phi 1 psi 3 mod square plus similarly the second term here in the denominator, third term in the denominator is like phi 2 psi 3 multiplied by its complex conjugate. So psi 3 acts on phi 2, so therefore you will have a number which is like phi 2 psi 3 mod square, and this overall thing is square root. So this is what would be the recipe for finding the orthonormal basis. Now it may happen that instead of only 3 vectors, because this is fairly general expression, right? In general, you may have a lot of vectors, say k vectors, right? And in that case, you should be able to generalize this into a expression which should look like, so let me just mark it in a different color because this is not applicable here. So in general, if there are more vectors, then phi k is going to look like psi k minus, so I think there are people who are joining now. Yeah, so we are going to have like phi k equals to psi k minus, you will have to project out about each of these vectors. So it's like phi, so you may have to choose a different index. So basically phi j acting on psi k and sum it over j equals to 1 to k minus 1. So that is what you would do. And in the denominator would be a norm of psi k with this quantity. So basically psi k minus sum over j equals to 1 to k minus 1, and you will have to project out the components along various axes. Okay, so this is in general the thing. So over here, if we go back to our original problem where we had a psi 1, a psi 2 and a psi 3 given, although it looks a straightforward implementation, but you have to be very careful while implementing it. Otherwise, there are all chances of missing out small factors here and there, numerical factors here and there. So like this idea that you will first find out phi 1, which is very easy. You are simply normalizing psi 1. The second, that you basically take psi 2 but subtract out from psi 2 the component along phi 1. So essentially you make phi 2 independent of phi 1. And then later on you like write phi 3 as psi 3 and subtract out projected components along the phi 1 direction and the phi 2 direction. So again, I think there are people, yeah, they're truly inconsiderate. Yeah, you have to be little considerate towards your classmates. Yeah, if you are on time, you are helping everyone, and we know that if there is any objection to having a class at any particular time, that should be stated in advance, not by coming late.
Sorry, sir. Sorry.
Like, I am not usually affected by thank you or sorry. So this is something which you have to learn if you are taking my classes. It is for your own benefit, right? For me, all of you are equal. So if you are on time, that just helps you and also saves time of your classmates. So let's just implement it and you will prompt me how we are going to find the corresponding orthonormal basis set. So let us write these vectors once again, just to make sure that we have things right in front to help us. So this was psi1, psi2 was psi3 was 1, 0, 1. So we straightforwardly know that phi1 is going to be psi1 divided by norm of psi1. So it's like we have a 1, 1, 1, but we divide it by, say, the transpose of 1, 1, 1. So 1, 1, 1 by 1, 1, 1. So this is a pure number and square root of that. So this is like 1 over root 3, 1, 1, 1. So we straight away know what is going to be phi1. Now phi2, we can write it as psi2. So psi2 is 1, 1, 0. And subtract from it phi1 psi2. So phi1 psi2 is going to be, phi1 is already there, so 1 over root 3. But now it is transposed, conjugated. So 1, 1, 1. And then you multiply it with psi2. So that is 1, 1, 0. And you find it along. So this is going to be phi2 psi3, and then this is going to be phi1. So phi1 again is 1 over root 3, 1, 1, 1. So that is there, and whatever comes, we'll have to basically find a norm of that. So in the denominator, it is going to be psi2 psi2. So essentially here psi2 psi2 means 1, 1, 0, 1, 1, 0. I'm elaborating all the steps because you will see for yourself that if you are not careful with implementing all the steps, there are high chances of errors happening. Okay, so minus, now we will have to take, so in this case it is going to be phi1 psi2 mod square. So basically mod square, but phi1 psi2. So phi1 is going to be 1 over root 3. And this is the bra vector, so this is 1, 1, 1, and psi2 is going to be 1, 1, 0. So 1, 1, 0, and then you basically do a mod square and root under. So essentially you can see that this quantity is going to lead us to a number which is going to be 1 plus 1, 2, and 2 by 3. So this is essentially 2 by 3. Right, and similarly, you can see that this is going to be 2 by root 3. So this whole thing is going to lead to 4 by 3. And this one is going to lead to a number which is 2. So 2 minus 4 by 3. So 2 minus 4 by 3 is 6 minus 4 is 2, 2 by 3. So root over 3 by 2 effectively. Root over the entire thing 3 by 2. So let's see how this essentially translates. So this is like 110 minus 2 by 3, 111. So that will lead us to a number which is like, okay, so that would lead us to a number which reads like 1 by 3. This is not the color. we were using this color. Yeah. So this is 1 by 3. This is going to be 1, 1 and minus 2. However, it has to be divided by the quantity in the denominator, which is going to be root over 2 by 3. Right. So it's better to place the equality sign somewhere around here. Yeah. So this essentially leads us to a number which looks like 1 over root 6 of 1, 1 minus 2. So one of the immediate consequences that you can check with phi1 and phi2 is both phi1 and phi2 are normalized now. So phi1 dotted with itself would lead to a number 1, right? 3 in the numerator and root 3 in the denominator. So therefore, like that's normalized. Similarly, over here in the denominator, there is going to be 1 over root 6 whole square. And in numerator, you are going to have 1 square plus 1 square plus a minus 2 square. So 4 plus 2, 6. 6 over 6 is 1. So that is kind of there. The other thing that you can check immediately is phi1, phi2. So you can check that phi1, phi2 is now 0, right? So basically, if you're saying 1, 1, the first two components in phi1, they are going to add up together. And the third component is going to lead to a minus 2. So 2 minus 2 is 0. So therefore, indeed, till this step, it is a set which is kind of the desirable kind. And then we need to find phi3. So phi3 is going to be, as we saw earlier, it is going to be, so let me rewrite that just to make sure that you recall and you are able to make a connection. Phi3, psi3 minus phi1 psi3 component about phi1 minus phi2 psi3 component about phi2 and then divided by the norm, which is going to be psi3 minus, we are going to have a phi1 psi3 mod square plus phi2 psi3 mod square. Right. So that put in action is going to look like we'll have a psi3 which was 101 if I recall. Yeah, 101. So therefore you will have a 101 minus, now you are going to have phi1 phi3 of phi1. So it is like 1 over root 3 whole square 1 over root 3 is 1 over root 3 is coming from phi1. So that is going to lead us to 1, 1, 1. So phi1 is going to be 1 over root 3, 1, 1, 1. Yes. And then we are going to have a 1, 0, 1. And then we again have a 1 over root 3, 1, 1, 1. So that's the first projected out component, and the second projected out component is going to be 1 over root 6 times 1 1 minus 2 with 101 times 1 over root 6 again a 1 1 minus 2. So 1 1 minus 2. So that is going to be in the numerator, and in the denominator you will have, I don't have to reiterate that a little bit of carelessness will lead you to completely weird quantities, and you will not be able to find out the right vector. So this was psi 3, the dot product of that, and then the first term, which is 1 over root 3 of 1 1 1 1 0 1, this whole thing mod square, and then the second one is plus 1 over root 6 1 1 minus 2 with 1 0 1. This thing again mod square, we have to close the middle bracket, we have to close the square bracket, and we have to put a square root. So basically 1 by 2. Yeah. So that would lead us to the quantities. So here again, let us check what's really happening in the denominator. So we can see that this quantity is going to lead us to a number which is 1 plus 1, 2. This quantity is going to lead us to a number 1 plus 1, 2 by root 3 whole square. So this is 4 by 3. And this quantity is, this entire thing is going to, including the squaring, right, would lead us to.
Excuse me, sir.
Yes.
Hello, sir. Rasmi is in, means he was unable to connect. He was saying.
Okay, he may be late, I think. Yeah, okay. So now this is the problem. You can see this guy is, Rashmi is coming with full privileges. Do you agree? So if I allow him, he immediately becomes the presenter. So I think, oh, he has vanished again. So has Rashmi joined now? No. Ask Rashmi to try joining in again.
Okay.
Right, he is no more. He's no more here. Okay. So we'll check that. So over here, what is the quantity? This is 1 plus 1, 2. 2 by root 6. Right, 1 plus 1 and minus 2. So minus 1 by root 6 whole square. So this is going to be 1 by 6. Okay. So therefore, in the denominator overall, like if you consider all these three terms, right, you come across, so 4 by 3, so it is 8 by 6 plus 1 by 6, which is 9 by 6, and 2 minus 9 by 6. So this is 12 minus 9, which is 3 by 6, and therefore this is 1 over root 2. Okay, in the denominator, this is going to be 1 over root 2. So therefore, if we try to kind of find this quantity, this is going to be, so we will have a vector which is having in the denominator 1 over root 2. So basically I multiply by root 2 here, and then over here 1 0 1 was surviving, but then I have a quantity which is 1 plus 1 2, 2 by 3, and you have to subtract it. So minus 2 by 3 from the first component, and then from the second component it is going to be 1 minus 2 is minus 1 by 6. So it is going to be 1 minus 2 is minus 1 plus 1 by 6. So this is going to be plus by 6. So that's what is the first component. The second component is 1 minus, this is going to be 1 plus 1, 2 by 3. So minus 2 by 3. And the third component is going to be 1 minus, so plus 1 by 6 of 1. So plus 1 by 6. And the third component is going to be 1 minus, this is going to be 2 by 3, and this is going to be 1 minus 2, which is minus 1, plus 1 by 6 of, so plus 1 by 6 times minus 1 by 6. So this is minus 2 by 6. So this is going to be 1 minus 2 by 3. So let me just write it slightly more neatly. 1 minus 2 by 3. You can go through this calculation again and check if any errors are made. So therefore this quantity is going to be, so if we take 6x as the denominator, so this is 6 minus 4 plus 1. 6 plus 7 minus 4 is 3 by 6. So this is 1 by 2. So the first term is root over 1 by 2. The second term is minus 4 by 6 plus 1 by 6. So that is minus 3 by 6. So minus half. And the third term is minus 2 by 3, and 2 by 6 is 1 by 3. So minus 3 by 3. So 1 minus 3 by 3 is 0. So this will lead us to 1 over root 2, 1 minus 1 and 0. So you can check that if this is phi 3, then you can check that phi 3 with phi 1 equals to phi 3 with phi 2 equals to 0. So that you can check. So phi 3 has 1 over root 2, 1 minus 1. So if we take it with phi 1, so it is like 1 over root 3, 1 over root 2 is 1 over root 6. And then there is a 1 minus 1, 0. So one of the component adds, another one subtracts. So overall it is 0. Similarly, 1 over root 2, 1 over root 6 is 1 over root 12. But then you have a 1 minus 1, 0. So again 1 1 minus 2 would lead to a 1 and a minus 1. So overall 0. So therefore we have achieved the orthonormal basis set. So this is a crucial thing. So let us just revise whatever we have done quickly. So what we were trying to do was ask a question about the procedure for Gram-Schmidt orthonormalization, and that involved distinguishing between linearly independent vectors and orthonormal basis set. So they are not the same. Linearly independent vectors does not mean that forms an orthonormal basis set. For example, you can have a set of vectors represented as 1 1 1, 1 1 0, and 1 0 1, which are called psi 1, psi 2, psi 3 respectively. So they are linearly independent. That is, psi 1 cannot be represented in terms of psi 2 and psi 3 and so on, like cyclic permutations. But if you try to find norm of psi 1, that is not 1, norm of psi 2 is not 1, and norm of psi 3 is not 1. So basically they are not normalized, and not all of dot products like psi 1 dotted with psi 2 or psi 2 dotted with psi 3 or psi 3 dotted with psi 1 are 0. So some of them may be 0, but not all are 0. So that essentially means that this is not forming an orthonormal basis set. So what would be the procedure? So that was that was provided by Gram and Schmidt. And then they started with linearly independent set of vectors psi 1, psi 2, psi 3 as given above. And like you can find out the procedure for finding phi 1, phi 2, phi 3. So the first step was phi 1 could be written as simply psi 1 divided by norm of psi 1. for finding phi2, what you do is you write down psi2 but subtract out the component along phi1 of psi2. So like this really helps us to make it linearly independent of like phi1. At the same time, the orthonormality is also ensured, and like orthonormality is ensured because you have projected out the component of psi2 along phi1 and you obtain a norm suitably. So the process for finding the norm is also written in the denominator here. That is, you basically take a dot product of psi2 with the numerator and take a square root. Similarly, phi3 can be obtained by writing psi3 and subtracting out the projections about phi1 and phi2 of psi3 vector. So that you do and take a suitable norm, and then you obtain. In case if we have more vectors, like this could be a k-dimensional vector space, then in general phi k could be written as psi k minus projection along each of these phi j's from 1 to k minus 1 and take a suitable norm. So that similar procedure was implemented here, and we found out for this given case that if we have psi1, psi2, psi3 given like this, you will reach a given set of orthonormal vectors. Now you can try on your own and show that this orthonormal basis set is not unique. Okay, so that can be obtained by simply permuting these three vectors. Like suppose instead of psi1 equals to 1, 1, 1, you can imagine psi1 equals to 1, 1, 0, psi2 equals to 1, 0, 1, and psi3 equals to 1, 1, 1, right? So therefore phi1 is going to be 1 over root 2, 1, 1, 0, right? And you can find out psi3 and psi1. So at least three different basis sets you can immediately demonstrate using this procedure. In existence of at least three different basis sets. However, there could be many more. So therefore, these finding an orthonormal basis set, whereas like it is important, it is not necessary that that basis set is unique. So that has several advantages, in fact, because sometimes certain basis sets lead to simplification of the results, like simplification of the calculations that we do. So therefore, we should not like we should rather capitalize on that. So that is as far as this Gram-Schmidt orthogonalization was concerned. Now let me come to a fundamental question. So this is the second part of today's talk, and that is asking, what do matrices fundamentally okay, it would really help if we use a different kind of a paper here, and the paper could be a checkerboard paper, because then we would be able to see all the matrix manipulations easily. So let me try to do that. So what I would do is I would first edit this by deleting these three. So let's have some patience while I do this. There should not be any mistakes committed. So now I will add some new pages. So what I do is add new page, and I would add something which is of the checkerboard type. Yeah. So let's just wait for a second till this is done. It's gradually becoming larger and larger in size. Yeah. So what the question that I was asking was, can we visualize the fact that how matrices operate on vectors and what do they really result in? So the question is, How does matrices operating on vectors a better question here? How does matrices, first of all, how does matrices operate on vectors? That's a trivial question. The question I want to formulate is how does matrices operating on vectors modify them? Okay, so that's kind of a question. It could have been framed little differently, but I think it expresses the concern which I am making. So let's take an example and let's see what we want to do. So let's consider a matrix. So it's always good to choose useful examples. So I have taken an arbitrary matrix, say 5, 3, minus 1, 1. And what I want to do is I would like to construct a scenario where I have two components of matrices respectively, two components of a vector respectively representing projections about two axes. So let's call this x1 axis and let's call this x2 axis, and let's consider a simple vector which we mark as 1, 0. So 1, 0 is this vector, right? So this is 1, 0 because what I'm doing is so this is 0, 1. So 0 projection along x1 axis and 1 projection about. So this one would be 0, 1. So I would not immediately write the, let me use a very faint color to basically mark it. So this is 0, 1. But I think that's not very visible. Let's not worry about it. What we want to do is we want to operate this matrix. Let's call this matrix M. And let's operate M on 0, 1. So this is same as 5, minus 1, 3, 1 acting on 0, 1, which is same as 5 minus 1 is 4 and this is 1. I hope I have not committed a mistake here. So basically what has happened is like matrix multiplication, I hope everyone knows. So
Sir,
operating M on
Sir, it's minus 1.
it's minus
so
one.
Minus
5
1 by 1.
just hold on. So 5 minus 1. So everyone knows matrix multiplication. So these kind of tricks I would, as I said, I would continue just to check if the class is alive. Otherwise, I would assure that things are not working. I would be assured of that. So how do you really multiply it? So you will multiply. So let's just kind of check this. So this is, so this is first row. I hope everyone knows this, but still there's no harm. So first row multiplied with first column, that would lead us to this member. And then if we are maybe multiplying this back with this, so this together will lead to the second member, right? So in this case, this is 5 into 0 minus 1 into 1. This is minus 1. And the other thing is 3 into 0 plus 1. So minus 1, 1. Ashna, is that the thing which you are saying?
Yes, sir.
Yeah, okay, minus 1, 1. Huh? So that actually tells us that now this vector, which was earlier this red vector, now this goes into minus 1, comma 1. So along the projection x1, this is minus 1, and along the projection x2, this is plus 1. So basically what has happened is this gets rotated. Okay, and this gets rotated by how much? 45 degrees. So essentially, like when you are applying M on 0, 1, this action is like rotation by, so pi by 2 is pi by 4, rotation by angle pi by 4, right, in a counterclockwise. So counterclockwise rotation by pi by 4. So let's see counterclockwise rotation. So this does two things, and that's where I want to check. So one is counterclockwise rotation of 0, 1 by pi by 4. That's one thing which it does. What is the other thing it does? Can somebody tell me what is the other thing this matrix does to 0, 1? What is the norm of 0, 1?
1.
Or 1, right? But what is the norm of minus 1, 1?
Root 2 or 2.
Root 2, right? So not only does it kind of rotate it counterclockwise, but also it scales 0, 1 by root 2. Okay, so these are two things. So any particular matrix in general will do either a counterclock, means either a rotation, either clockwise or counterclockwise, or scaling of the vector, or both. Fine, so this fact is accepted, right? You saw it in action. Now let us just take another example. Say, so this was case 1. Now let's take, say, M acting on 1, 0. What does it do? Say it's like 5 minus 1,
Hello?
3, 1.
Hello,
Yes,
sir. Sir,
yes, yes, please.
maybe Rahul got disconnected and he is in the
Oh,
lobby.
oh,
Can,
I see, I see, I see, I see. I'm so sorry. I did not disconnect him. Okay. So I have added him. Okay.
okay, sir.
So 5 minus 3. Thank you so much. Aradhana, you are very helpful on these. I mean, the entire class is very helpful on these matters. Thank you so much. Please keep doing that. Okay. So when we multiply this M with 1, 0, what happens really here? So now the class is awake. This is going to be somebody from physics. What is this going to be?
5.
5, 3. Right. So this vector now goes over to something like, so this is 1, 2, 3, 4, 5 and 1, 2, 3. So it really goes this long. Right. So now there is again a rotation plus scaling. Fine, you can see that it is again a rotation plus scaling. So here I would just like to tell you that you can try this operation on a wide variety of vectors, right? Wide variety of vectors. Any vector you can choose in this vector space and operate this matrix on it. But now I will tell you an interesting set of matrices, like an interesting set of vectors. Say suppose I choose my vector to be 1, 3. 3, 1, acting on 1, 3. I am sure, although this may be looking very simplistic till now, but very soon, at least the physics students would be in awe that, okay, we did not realize or we did not really think it that way. Or even math students, I hope they would not have visualized or would not have imagined the concept that we are going to develop with this simple analogy. Like they may not have thought about it, although they would have done reasonable number of linear algebra courses. So here, what does it do? Like if you say 5 into 1 is 5 minus 3, so that is 2. And what is this? 3 plus 3 is 6. Right, so this is like twice of 1, 3. So basically what it does is, if the initial vector was like, so okay, so here we have to understand that we must pair them. So I'm sorry, in the diagram there is a small error. What we have to do is we have to small error in the sense that there could be a chance of confusion. So what we are looking at is trying to see what happens to the red vector and what happens to the purple vector, right? So let them be paired up as red and purple. Like that will ensure that we are not confusing ourselves. And similarly, in the second case, it was 1, 0. So 1, 0 is this vector. So in purple color, this would be like 1, 0. And 1, 0 goes over to this vector, which I think, let us just erase this a little bit and redraw it. So this is 5, 3. So this goes straight from here to here. So whatever was this vector, this goes to there. Huh. So now we are trying to look at a vector which is 1, 3, right? And let's draw it in a kind of fluorescent color. So 1, 3 is 1 and 3. Right, so this vector looked like this, right? But then what has happened when we kind of operated this matrix M on it? It just scaled. Okay, it did not rotate. So here what is happening is only scaling. Right, only scaling of the vector, no rotation. Now let's do one more thing, and let's choose another vector which I hope I have kind of cooked up properly. So let me just to illustrate this example. Yeah, yes, please.
So in the this example, the green one, that you say that 360 degree.
Pardon?
There is a rotation of 360 degree. Means there also be the same.
Okay. So we will not go. That would be modulo 360, right? So we are not going into that right now. Okay. So that way, if you say multiplying by 1, say for example multiplying by iota, right? You would have seen that was equivalent to rotation by pi by 2. Fine. Say 1, if we multiply, it becomes in imaginary axis an iota. And if you multiply by another iota, it is like another rotation by pi by 2. So it becomes a minus 1. 1 becomes a minus 1 if you rotate it twice. Let us see, somebody else has again joined. Okay. So of course that is there. And then if you multiply thrice with iota, that is like 3 pi by 2 rotation. And then if you multiply by I to the power 4, which is again 1, there is a 360 degree rotation. So that of course is there, but we are excluding that scenario. Okay, so we are not really worried about that at the moment. So let us see what we are worried about. So
Okay.
let's see what happens. What happens when we are multiplying this number 5 minus 1, 3, 1 with 1, 1. right? So this is like 5 minus 1 is 4 and 3 plus 1 is 4. So this is like 4 comma 1 1. So it is as if we are putting a vector. So now let's choose a suitable color. Let's choose this color to distinguish. So oh no, this color would not be very useful. So let's choose maybe brown. Yeah. So if we have this vector which was 1 1, right, to begin with, now what is happening is it is simply scaling by a factor which is like, right, 4 4 4 comma 4. So these two vectors are unique. These two are special. They only scale when the matrix is operating on these vectors. Okay, and such vectors which don't undergo any rotation but only scale, right? Even if you are saying rotation, that would be 360-degree rotation, right? So there is no rotation modulo 360. So therefore, like such vectors are having a special name, and these are called eigenvectors. Okay, so this is eigenvector, and these numbers which you saw 2 and 4, they are the corresponding eigenvalue. Fine. So physically, whenever you are imagining a vector, like we have just imagined a vector in two-dimensional scenario, right? It could be an n-dimensional vector or an infinite dimensional vector. But accordingly, like we will have to think about corresponding rotations in such spaces. Right now, we are thinking about rotations in two-dimensional plane, right? We can also, therefore, we will have to extend our imagination to rotation in n-dimensional space, or for that matter, eventually for quantum mechanics in n-dimensional Hilbert space. Rotations in n-dimensional Hilbert space and scaling in n-dimensional Hilbert space. So the vectors which undergo no rotation but pure scaling, right? Occasionally the scaling would be by a factor of 1 itself. In that case, the eigenvalue is going to be 1, right? So this vector remains unchanged essentially. So that is like scaling by 1 and rotation modulo 360. So therefore, like such vectors are called eigenvectors. So we can quickly try to see that indeed that is the case. So for this vector, we know that we have earlier seen a recipe for obtaining eigenvectors. So let's see. If lambda is eigenvalue, we know that determinant of m minus lambda identity is equals to 0, right? Which is like determinant of, or I can simply use the symbol. So this is like 5 minus lambda, 1 minus lambda. Somebody can please unmute, like mute themselves, because there is a noise. Accidentally, somebody has unmuted. So if you can mute yourself, yeah. So 5 minus lambda, 1 minus lambda. You have 3 and minus 1. I don't know what happened here. Yeah, okay. Yeah. Oh, this happens to be some funny patch. Let's forget it. Yeah. So this is like 5 minus lambda and 1 minus lambda. 3 and minus 1 equal to 0. Right, and that will tell us that 5 minus lambda into 1 minus lambda plus 3 equals to 0. right? And that is like lambda square minus 5 minus 1 minus 6 lambda square minus 6 lambda plus 5 plus 3 8 equals to 0. It implies lambda is going to be minus b, so 6 plus minus root under b squared 36 minus 4 ac 32 by 2a. So this is like 6 plus minus 2 by 2. So 6 minus plus 2, 8 by 2 is 4. And the other one is 6 minus 2 is 4 by 2 is 2. So therefore we can see that we indeed had an eigenvalue 4 and an eigenvalue 2. So we have obtained the eigenvalues, right? These were the eigenvalues. And accordingly, one can also find out what would be the corresponding eigenvectors. So for that, let V1 be an eigenvector, which is say A, B. Then it implies, like say for lambda 1 equals to 4, right? Let V1 be the eigenvectors. So that simply means that we have a situation 5 minus 1, 3, 1. So this is like 5 minus 1, 3, 1 acting on AB equals to 4 times AB. Right, so that would mean 5A minus B and 3A plus B equals to 4A, 4B. So this leads to two equations, which really implies 5A minus B equals to 4A. So that's like 5A minus 4A is A equals to B. And similarly 3A equals to 3B. So therefore, like one of the typical eigenvectors could be, without normalization, could be 1, 1. So that is what was the corresponding eigenvector for 4. Similarly, you can show that eigenvector for lambda equals to 2 is going to be like this. You can just check, but this is going to be 1, 3. So 1, 3. So like to summarize, what I wanted to convey was these eigenvectors are special vectors corresponding to these matrices. In the language of quantum mechanics, it is like if you have an eigenket, right, and the corresponding Hamiltonian matrices. So Hamiltonian matrices have only, or Hamiltonian operators have the only role of scaling these eigenvectors. They cannot rotate these eigenvectors. So that has many interesting implications in quantum mechanics and eventually in fields like quantum information and so on. So I think we will stop here. Thank you so much. Questions?
Sir?
Yes.
So in mathematical language, we take that the eigenvalue should belong to a field and that eigenvector should be non-zero. So it is the same case we will discuss here.
Okay,
So
yes.
here
Yes.
also eigenvector should be non-zero and the eigenvalue belong to the field we have taken.
Right. Right,
Okay.
you're right. You're right. So we will get an opportunity to practice some of this in Mathematica also, some of the problems. But like in the numerical techniques part, what we will in addition learn is how to implement these diagonalization subroutines or eigenvalue, like basically obtaining eigenvalues. Because one of the approaches to diagonalization is if you know eigenvalues and if you know eigenvectors, you can construct a set of matrices with the help of which you can diagonalize the matrix. Okay, so or essentially the other point is, if you are able to diagonalize a matrix that is equivalent to all the diagonal elements are going to be the eigenvalues, like all the respective eigenvalues. Fine. So there are recipes, well kind of evolved recipes for obtaining eigenvalues and eigenvectors. And the purpose in this course would be to ensure that whenever we are using a package like Mathematica or MATLAB, we are not simply kind of using them as some kind of libraries, like some kind of executable programs. But we also know underlying that what phenomena is happening, like what is happening realistically. Okay, and that realization is very helpful when you are doing when you try to do good science. It is very important to have that realization. Okay, thank you. I did not keep an eye on the clock, but it turns out we have just finished in 1.5 hours, and some of you will have to leave for the next class.